Hello everyone. Today I'd like to introduce our new project in Pasir Gudang. We are proposing a 5.3 hectare pharmaceutical manufacturing plant, which will house a heavy load logistic warehouse, a two-story administrative block and key utility infrastructure, as shown in the satellite map on the right of image. The site is located in a premier industrial area but face unique geotechnical challenge. Its critical proximity to Sungai Kim Kim means we must carefully manage highly sensitive waterlogged riverine conditions and potential soft clay zones. The main geotechnical challenge here are a shallow groundwater table at 0.5 meter depth and a 10 meter depth alluvial soft clay layer with critical low shear strength under 25 kilopascal. This creates a high risk of severe differential settlement and bearing capacity failure. Our mitigation strategy is threefold. First is implement ground improvement using PVD with preloading. Second, utilize deep piling foundation for heavy structure to bypass the weak soil. And third, construct a robust drainage system to manage groundwater levels.
Good morning to the panels. Today, I will present Chapter 2, Causes of Problem for our factory project near Sungai Kim Kim. First, let's look at our substructure reality. From 0.5 meters to 10 meters, we are dealing with a critical soft clay zone. This alluvial soil has a very high moisture content of over 70% and extreme low shear strength of less than 20 kilopascals. Furthermore, our chemical analysis shows a high hydrostatic threat with elevated sulfite levels exceeding 1,500 milligrams per liter. This aggressive chemistry is caused by the surrounding river geology and historical industry activities in Pasir Gudang. Mechanically, if we apply heavy structural loads, it triggers primary consolidation settlement. This process is governed by Tegazit effective stress principle. As shown in the spring analogy model, the massive loading forces the poor water out of the clay. This causes severe ground compression, leading to an estimated structural settlement of over 420 millimeters and a high risk of slope failure toward the riverbank. Chemically, the high sulfite water will cause a concrete sulfite attack. The sulfite ions react inside standard concrete, creating internal expansion, heavy cracking, and structural softening from day one.
Effect problem. The foundation instability caused by soft clay plus high groundwater equal to low bearing capacity and high compressibility, about 420 millimeter deficient settlement, deficient for farmer facility. Next is obstacle persistent saturated ground equal to compaction roller fail and require cost drainage solution. And next is SE and environmental danger. This is runoff tracker Sungai Kim Kim, and the toxic gas release rates from this being very chemical pocket.
We have three proposed solutions for this site. First is PVD plus preloading, which accelerate 50% of water drainage from decades to 9 months for cost-effective large area treatment. Second is vibro replacement using stone column to provide a dual mechanism of direct load transfer and continuous water drainage. Third is deep soil mixing, which chemical binds the clay with cement to instantly create high strength load bearing support.
Now, I will continue with Chapter 5 for the deep foundation strategy. To bypass this weak alluvial layer, a shallow foundation is impossible. We must transfer all structural loads deep into the hard bedrock where the SPTN value is greater than 50. Our team selected a hybrid deep foundation strategy. We will use driven reinforced concrete RC piles for the main warehouse area because they offer excellent load capacity and high cost effectiveness. However, near the sensitive Sungai Kim Kim riverbank, we will strictly use bored piles. This is a strategic choice because boring works produce low vibration and low noise, which protects the fragile river slope from collapsing during installation.
Okay, next, the slides present the key socio-environmental conflict identified in the project, which are contaminated groundwater released during PVD installation and river pollution during the SM operation. For conflict 1, contaminated groundwater released during PVD installation may cause water quality deterioration, ecosystem disturbance, and biodiversity loss. Socially, it can create public concern and negative perception towards the project. To mitigate these impacts, a line retention pond and an on-site water treatment plant are proposed before the water is discharged. Next, we're moving to conflict number 2, Drought spoil runoff from DSM operation may increase water turbidity, elevate pH level, and degrade aquatic habitats. It may also lead to public complaints and regulatory action. This impact can be reduced through ban, spoil pits, and proper waste disposal. In conclusion, proper foundation selection, effective construction planning, and suitable mitigation measures are important to ensure a safe, sustainable, and successful project. Thank you.